Good evening, students. Today, the topic of discussion is free body diagrams. There are several problems which arises from free body diagrams, and it is observed that free body diagrams forms an integral part in solving the mechanics problems. Now, towards it, let us understand first what do you mean by free body diagrams. Okay, now go to the next slide. If I have an object of mass m, and let us say it is kept on a table. Now this will be subjected, okay, now if it is at rest, for example, it is subjected to two forces. The first force is nothing but the mass of the object is here. So as a result of it, you can observe that there is an force mg acting downwards. Now in addition to this, okay, if there is a force mg acting here, this should actually penetrate this table or break open the table, and as a result of it, it should fall down over here. But it doesn't fall. What is the reason behind it? Because the surface here also opposes this object in the opposite direction. So thus the opposite force here is nothing but the normal force. Now the normal force is nothing but the force acting on the surface. Thus you see this normal force and mg force both are equal and opposite to each other in this example, and thus you can now write from this expression that n is equal to mg. Now before we write this, what we have done, let us understand this. We have just taken an object, we have drawn the total forces acting on the object, and finally arrived at an equation over here. Now also look at it that the object is in equilibrium here, and as a result of it, I have just equated it just like this. N should be equal to mg, and as a result of it, okay, it does not move. That's what we have said. And I have done it only along one direction, along only one line, see, along y-axis. I have not done it along the x-axis. Can you reason why? What is the reason? The reason here is because there are no forces acting on the x-axis. There is only one force here, which is acting along the y-axis. As a result of it, I have got this. Now, let us say, for example, let me complicate this problem a little bit. Now, I have this is my surface, kept the object over here. I put a thread here, and then I try to pull the object like this. Now, what do you expect? What are the forces? Okay, let us draw the free body diagram for this. Now, in a free body diagram, the result of a free body diagram or the consequence of a free body diagram is to arrive at a force equation. The first thing that we need to do is assume that how much ever large an object is from a point, find out what are the forces acting at this point. So towards it, the first force, as you observe here along the y-axis, is nothing but you have one force which is normal force acting upwards, and you have another force, mg force, which is acting downwards. And then at the same time, I said that I'm going to apply a force over here. Let me say I'm applying a force of F here. And then, okay, I expect this to move. So because in the absence of any other opposite forces over here, I should expect the object should move. If the object is not moving, that means there's one more force in the opposite direction. Now what we do is, let me assume that this force is acting here and the object is not moving. When the object is not moving, which means the additional force acting in the opposite direction is nothing but your frictional force. See, frictional force is acting here. You should illustrate the forces, the directions appropriately at the correct places. If you write the frictional force over here, which means you are making an error. So this, you will not get a mark here. You should always indicate the frictional force in this direction, and that too below over here. Okay. Now as a result of it, now what is the status of the object? The status of the object is, once again, it is at rest, or the right word here would be equilibrium. It's in equilibrium. As a result of it, now I need to write the force equations. See, the purpose of writing a free body diagram is to write a equation, a force equation. So towards it, now I will have force equations. How do I write it? Now you see, there are two forces acting along the y-axis. There are two forces acting along the x-axis, right? Of course, this line is parallel to this, so therefore still we can consider the x-axis. Okay, so as a result of it, let us write down the y equations. So now let me write n is equal to mg. Okay, this is nothing but the forces along the y-axis, and F is equal to frictional force. This is along the forces along the x-axis, right? So therefore, I have drawn the forces acting on both y and x-axis, and as a result of it, the object is not moving. Okay, let me take up one more example. I put an object here. I apply a force of F1 like this, F2 like this, but there is one more force, F3, which is acting here. And I observe that the object is still in equilibrium. All the examples in the slide refer only to equilibrium. Okay, F1, F2 is applied, F3 is applied opposite. And then you observe what are the other forces acting here. See, I have drawn only 2-3 forces over here. The other forces I have put across here is, this should be mg acting downwards, and from here, normal acts upwards. Thus, now let us write the force equations here. What are the force equations here? You can now write N is equal to mg, and then F1 plus F2 is equal to F3, right? So thus you see the magnitudes of these forces, they should be equal to each other, right? So we have arrived at the third one also. Not quite complicated, okay, quite easier. Now let me write one more diagram. Now let us say, for example, I have a string, I have another string, and I have an object which is hanging like this. And this is in equilibrium. See, I have taken all the cases examples as equilibrium only. Okay, this could be your MCQs. Now, as a result of it, this again has a mass here. So therefore, can you think about what are the forces acting here? So now let me say this is connected to a ceiling. It's connected to a ceiling like this. Connected to a ceiling like this. Now you see, mg force is acting downwards like this. And you observe that this is my tension force. This is my another tension force. This could be T1 and this could be T2. Now, can I write T1 plus T2 equal to mg? I will not be able to write. So if I write T1 plus T2 is equal to mg, this relationship is incorrect. Why do I say it's incorrect? The reason is because T1 and T2 and mg, they are not along the same line. See here, F1, F2, F3 I have equated. I have not equated F1 plus F2 plus n is equal to F3 plus mg. I have not done that, right? I have done it only for the forces that are acting along the same line. Now you see, the forces are not acting along the same line. See, this force is acting like this force is acting like this, is acting downwards. So I will not be able to write this equation. This equation is definitely incorrect. Now towards it, if I want to write it correctly, what I need to do here is that now draw a vertical like this. Draw a vertical like this. Usually, this angle would be given. This angle would be given. Let us say, for example, I give you an angle equal to 60 degrees here. This also 60 degrees. Now, the first thing is that if these two are 60 degrees, now you see this length should be equal to this length, because you see this should also be 60 degrees. Do you guess why do I write like this? Because it's nothing but an equilateral triangle here, right? So if this is an equilateral triangle, then the tension acting here and the tension acting here should be one and the same, because the lengths are same, so it should be same. The T1 should be equal to T2, but still I cannot substitute here. I'm incorrect, right? So this one I have deduced from here. Next, what I should do is, if this is, now why should this arrow be like this? Many of them write the arrow like this here. Okay, this arrow is incorrect. Why is it incorrect? Because tension is a pulling force. Pulling force. Now you see, for this object is being pulled upwards like this, pulled in this direction. Though if it has been pulled like this and pulled like this, then it should go upwards, right? But why doesn't it go? Because it has a mass m, and that is pulling downwards over here. As a result of this, okay, it is at rest. Now towards it. Now this is my tension T1. This is my angle 30 degrees. This is 60. This is 90. This should be 30 over here. So as a result of it, I will take, this is a vector quantity here. I'll take the component of this vector along this direction, which should now be equal to T1, okay, along the upward direction. The component of this vector along this direction should be T1 cos 30. In a similar way, so if this is 60, see this whole thing is 60. So therefore, this is bisected over here. This is also 30 here, right? This angle is 30. See, this angle is 30 here. Okay. So therefore, this once again gives rise to one more T1 cos 30. Now you see, there are T1 cos 30 and T1 cos 30, both are acting in the same direction. So therefore, along this line, okay, so you have, this is the mass, mg is acting downwards. I have represented this one by a point. And then at the same point, you observe that there are two T1 cos 60 which are acting here. Cos 30, sorry, T2 T1 cos 30 are acting over here. Thus, I will be able to write, since the object is in equilibrium, 2 T1 cos 30 is equal to mg. In many of the problems, they will ask you what is the tension acting on these things. So making use of this, I can now write 2 T1 into root 3 by 2 is equal to mg. This goes away. The T1 should be equal to mg by root 3. I hope you understood this. Now, many of you will be asking the question, see, I have splitted this tension into two parts. Okay, one along the y-axis here, the other along the x-axis over here. Now, what happened to the x-axis? Now, this should be T1 cos, T1 sin 30, and this side should also be T1 sin 30. Now you see this T1 sin 30 and T1 sin 30 are in opposite directions. As a result of it, they cancel each other. And hence, no net force is acting along the x-axis. Okay, and then you see the net force acting here, okay, is 2 T1 cos 30 upwards, which should be equal to mg. I hope you understood about this problem. Okay, based on this problem, let us solve about the other problems also. Now, so far, what did we do? The fourth example that I have shown you was something like, there was an equilateral triangle. Equilateral triangle. And then as a result of it, I said that the tension here and the tension here were seen to be one and the same. It did not vary. Next, now what we'll do is, let us say they are not equilateral. Fifth problem. So one is like this. The object is hung here. The other one is like this. Now, can you think of what could be the tensions? Will the tensions be equal? Okay, the MCQ that you can get here is that they can ask you whether the tensions can be equal in this diagram. There are two strings. Let us say, for example, this point is O, OA and OB are two strings. Now, will the tensions in both the strings be equal? They can give you something like the length of the string is seen to be 5 centimeters. Length of this string is seen to be 15 centimeters. Then in that case, let the tension here be T1, let the tension here be T2. They will ask you whether T1 is greater than T2, T1 is less than T2, T1 is equal to T2, or T1 by T2 is equal to, just a moment, yes, T1 by T2 is equal to 1 by 3, because you see 5 by 15. Okay, something like this they will ask you. In that case, how do we do this? Now towards it, see, definitely T1 is equal to T2 is impossible because they are not an equilateral triangle. Now let us understand what happens. Let us say, for example, if they give you angles like this angle is, what can this angle be? Let us say, for example, this is 45 here. This is 45 here. This is something like 70 here. So how much will this be? 45 plus 70. 45 plus 70 would be 135. 135, 145, 155, 165, 175, 180. Then what will this be? 40 plus 70 is 115, right? I'm sorry. Yeah. Okay, this is 115. 115, 180 minus 115. Just a moment. Okay, I'm back. So this is 65 degrees here. Now you see the angles are different. It's a scalene triangle here. Okay. So if I want to find in this case, now what will happen? So now what we do is, let us draw the diagram separately. This, let me call this as T1. This, let me call this as T2. Definitely T1 and T2 are different. Let me put it like this. Okay. And this is my object. Now towards it. Now is this bisected? Definitely not. They are not bisected. If I put it like this, you see, there's some angle here, there's some angle over here. And then the total angle is 70 degrees. And this angle is 90. And this angle is 65. This angle is 65. If this is 90, 90 plus 65 would be 155. 155, 180 minus 155 would be around 25. This would be 25 degrees. If this is 25, then this angle would be, this angle is 45 now. This angle is 45. And this angle would be how much? 70 minus 25 would be 45 once again. And this is 90 once again. Now see, we have got the respective angles over here. So towards it, now let us resolve the force. Okay. The component of T1 acting along this direction should be T1 cos 45. And the component of T2, now this is T2. T2 along this direction should be T2 cos 25. Okay. And now we know that with respect to this, there's an mg here. So I can now write this as T1 cos 45 plus T2 cos 25 is equal to mg. I'll be able to write this. Then now let us resolve this in this direction also. Now in this direction, it should be T2 sine 25 and this should be T1 sine 45, right? So T1 sine 45 should be equal to T2 sine 25. And assuming that this is an equilibrium, okay? And then what we have is, what is that we need? We need to know whether T1 by T2 is less than 1, greater than 1, whatever it is. So T1 by T2 will be equal to sine 25 by sine 45. Okay. Now, if you find out what is this value, sine 25 is closer to sine 30. It could be, you may have a value equal to 1 by 2 over here. And sine 45 is nearly 1 by root 2 over here. Okay. So as a result of it, you will get this as 1 by 2 multiplied by root 2 by 1, which will now be nearly equal to 1 by root 2. Okay. Or maybe you will not exactly get 1 by root 2. You might get something like, this could be around, not be 1 by 2, this will be 1 by 2.5 or something, 1 by 2.5 or something. So this should be root 2 divided by, okay, 2.5 or 1.4 by 2.5, nearly somewhere like this, you get it. So definitely this answer is incorrect. And moreover, you see here, T1 by T2 is definitely less than 1, right? Okay, so as a result of it, T1 by T2 is less than 1. So this answer is the right one. This is the incorrect one. So this is the way how you can solve problems using free body diagrams. Let me show you some more free body diagrams. Okay, now sixth problem. Let us say I have an inclined plane. Inclined plane. The angle here is 60 degrees. And I'm putting an object over here of mass here. Now, let us say the object slides down. Why should the object slide? The simplest reason here is that gravity. You will all answer about gravity. Where is the gravity acting here? Gravity is acting downwards over here, right? mg is acting downwards over here. If mg is acting downwards, why should the object slide? Any answers? Now you see, it will slide. The reason is because the component of mg is acting here. See, whenever there is a force is a vector. When you have a vector, you can resolve them into components along the x and y axis. We always say x is along this line, right? X is along this line and y is along this line. But unfortunately here, we don't take like this, but instead, for the sake of solving the problems, we consider the x-axis is along the plane and y-axis is perpendicular to the plane. That's what we do here. Okay. And then as a result of this, now if this is mg, okay, let me write it down. This is mg. I'll put it like this. So this angle is 90. This is 90. This angle should be 30 here. You see, 60 plus 30, 90, 90 plus 90, 180. Right? So we have got this is 30. This angle is 30. Let me extend this line backwards. See, this line is perpendicular to this one, right? As a result of this, if this is perpendicular, you see, this line is perpendicular. This line is perpendicular here. So if this angle is 30, then this angle should be 60 degrees over here. Let me write it down once again. I have the object here. I will write one line like this. I'll write one line like this. I'll write one line like this. Identify this. This is my normal force. And this was my object. This was my object. And this was the weight acting downwards, mg. And the angle between these two lines is 30. Angle between these two lines is 60. So as a result of this, this mg is acting along this direction. The component of mg acting along this direction should be mg cos 30. The component of mg along this direction is nothing but mg cos 60, right? And then now as a result of this, now there are two conditions. The first condition, it's in equilibrium. It is not moving. Okay, but that's what we had been doing. Now, why doesn't the object move? The reason is because there's somebody who is pulling it like this. Is there somebody pulling here? I have not told you anything about it. So it is evident that there is a force which is acting like this, which is nothing but your mg cos 30. So this should move. But if it is not moving, that means there's something which is pulling it backwards. What is that? Frictional force, right? So therefore, I can write one more force over here. So this is how you identify the missing forces. Okay, looking at the nature of the object, whether the object is moving or not, you identify the correct force. So thus now let us write the free body diagrams. You see, this is my y-axis and this is my x-axis, right? So this is my x-axis and this is my y-axis. Y-axis. Now let us write down the equations. Now this is an equilibrium. So I can now write n is equal to mg cos 60, which means it should be mg into half, which should be mg by 2. This is something which you need to realize here. So usually when we write normal forces, we always assumed in the beginning that normal force is equal to mg. They are equal and opposite, but that need not be true always. See, normal force here is equal to half the times the value of mg, right? Okay, then let us look at this here. Now you see, mg cos 30 is acting like this, frictional force is acting like that. So mg cos 30 should be balanced by the frictional force, or the value of the static friction is seen to be mg into root 3 by 2. Okay, so mg into root 3 by 2 is nothing but the value of the static friction. So see, we have understood about several concepts making use of the free body diagrams. Let us solve one more. Let us take a wedge like this. And let me say I have a sphere. I have a sphere which is touching the surface like this, or maybe a rock or a boulder is touching the surface like this. This is a mass m. Now draw the free body diagram for this. The angle here is seen to be 60. This is at 90 degrees. Okay, and this should also be how much? 30 here, right? Okay, and towards it, because 60 plus 30, 90, 90 plus 90 becomes 180. Now, where are the forces acting? The first thing is, now this is standing on the earth. As a result of this, the mg force will always be acting like this. You cannot defy that. Now, the mg force is acting here. Then what about the other forces? Okay, they should actually break this wedge and come down, right? But it's not happening. There are two supports here. Okay, this is supporting this. That's what we can say. Now, when I say supporting, what does it do? It is holding it, which means it's trying to push it like this, right? So therefore, the point of contact. Okay, so you have to draw the normal force. Remember, you are not going to draw the normal force here, which is incorrect because the object is not in contact with the base here. You are going to draw a normal force like this, which is N1. You are going to draw one more normal force here, which is N2, here, right? N1 and N2 are shown to you, right? Now, what next? Okay, have we done with it? Because we need to draw the FBD and finally arrive at the equations also. Now, how do I arrive at the equations? Now, towards it, let me drop like this. So if this is 90, now what do I need to do? Arrive at a force equation. I should see to it that the upward force should be equal to downward force, or they should be acting along the same line, right? So therefore, let me resolve this. I should draw a perpendicular like this. And then I should say that this normal force is now going to break down along the horizontal all along the vertical directions. So towards it, I need to find what is the angle between this perpendicular line and the normal force. How do I do it? Now you observe this angle is 90 degree here. And then if I drop a perpendicular here, okay, the diagram looks like this. If I zoom in, the diagram looks like this. This is my 60. Now, this is 90. This should be 30 here. Right? This angle is 30. And then this angle is 90. Okay, so I have to draw this one here. This is my perpendicular normal, N1 here. So this angle is 90. So if this is 30 and this is 90, then this angle should be 60 here, right? 60 plus 30, 90, 90 plus 90, 180, full angle, 60 degrees over here. Now, if I draw a horizontal like this, then you see if this is 60, then this angle should be 30 here. Now, this is a normal. So now what I can do is I can write along this direction, I should be writing this as N1 cos 60. And along this direction, it should be N1 sin 60 or N1 cos 30. I'll be able to write like this. I have splitted the normal force into two parts. Okay. And then now let us take up this boulder. In this boulder, now what do I have? Once again, this is my normal force. This is my normal force N2. This is my upward direction of the line. And this is the wedge that has been shown. This is the angle 30 here. And then I will draw a line like this backwards. And you see that if this angle is 30, and I have also mentioned this is 90 degrees, let me take this also as 90 here. Okay, I am just giving some angles. Okay, it is not that every time it has to be 90. I am just taking some angles for the sake of easiness. So if this is 90 degrees over here, if this is 90, this angle should also be 90 here, right? When this angle is 90 degrees, now what can happen is that, now how do I arrive at it? I will drop a perpendicular like this. If I drop a perpendicular here, if this is 30, this is 90, this angle should be 60. If this angle is 60 and this is the angle is 90, then this angle should be 30. Why 30? Because you see 30 plus 90 plus 60 should be equal to 180. Straight angle, right? Okay, we have got all this now. Then if I follow the same rule, draw a line horizontally. Okay, you should actually practice it. Okay, just by looking at it, you will not get to know. When you are solving this problem, see to it that you practice it on hand. If this angle is 30, this angle should be 60 over here. Now towards it, this is N2. I will be able to write N2 cos 30 upwards and N2 sin 30 in this direction. Now you see there are two forces acting on the boulder. What are the forces? Upward forces. Upward forces are N1 cos 60 due to this plus N2 cos 30 should be equal to mg. We have got the first force equation. Okay, you can substitute the values. This will be 1 by 2, this will be root 3 by 2. Thus you will be getting N1 plus root 3 N2 divided by 2 is equal to mg. This will be your first equation. The second equation tells you that this is in equilibrium, and as a result of it, N1 sin 60 should be equal to N2 sin 30, right? As a result of this, you will be able to write N1 into sin 60 is root 3 by 2 should be equal to N2 into half. This goes away, and thus you will be able to write N1 is equal to N2 by root 3. Then you can substitute one with the other and finally solve the equation. Isn't it interesting? Okay. So now we have learned free body diagrams, how to write the free body diagrams in case of stationary objects. Okay. If you are able to understand and solve all these 6 or 7 problems that we have done so far, you will be able to draw free body diagrams for any stationary object. Okay. Now let us do, or maybe I will stop here. Okay, so do understand this. Now provide your feedback on the text boxes provided below so that I can get to know, okay, where did you get confused? It's a good revision exercise to work with. I had done the same thing in the class also, except for this particular problem. So you can try it out and let me know. So tomorrow I will be uploading one more video on free body diagrams, wherein we have a pulley system, we have a spring system, and then when the objects are moving, how do you write the free body diagrams? Thank you.